Well, we've talked about defects in Hamilton's method, and for that reason, Hamilton's method is no longer used. More recently in American history, we've been using these divisor methods. We're currently using the divisor method to apportion the House of Representatives. So, what are divisor methods? Well, first of all, let me tell you what they are not. They are not quota methods. In other words, these are not methods that come with a guarantee that every state is given either its lower quota or its upper quota, by which I mean lower standard quota or upper standard quota. And what do they all have in common? Well, they all say don't have leftovers. Rather than worry about how to distribute leftover seats, they say let's not divide necessarily by the standard divisor, let's divide perhaps by some other divisor so that there are no leftovers. We're going to learn three divisor methods in this order. First the Jefferson method, then the Adams method, and then the Webster method. Now they're very similar. In fact, the only way that they differ is that they use different rounding rules. Now, to actually use these in practice, we're going to have to adjust the divisor. Okay, rather than using the standard divisor, we'll have to use some other divisor. How do we discover it? We're going to discover it by a guess and check procedure. We'll try out divisors until we find one that works the way that we want it to. First of all, Jefferson's method. Jefferson says always round down. Take your quotas and round them down. Now, of course, some states deserve an automatic one seat. If we would round down, they would get 0. So, of course, remember to give out those automatic ones. But for all the other states, do this rounding down procedure. Now, we know what's going to happen if you follow this prescription using the standard divisor. Namely, you won't have given out all the seats. You'll have leftovers. And Hamilton says, well, here's a way to give out the leftovers. Jefferson says, no, 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 no. We don't want to do that. We don't want to have leftovers. He says what we should do is we should alter the standard divisor until the rounding down works out just right. If the quotas are coming out too small, which they will when you try the standard divisor, then we need to make them larger. So we need to decrease the divisor from the standard divisor, but we don't want to go too far. It's like Goldilocks. We need to get exactly the right size. If our divisor is too big, then we'll have leftover seats. But if our divisor is too small, then we'll have assigned too many seats. What we want is to get our divisor just right. We'll distribute exactly the right number of seats in that case. Now I'm going to demonstrate how this works by using the actual 2010 census data. I'm going to apply Jefferson's method to it. To automate these calculations, I'm going to be using a spreadsheet. Here's the spreadsheet. In column A, we have the names of the states. You need to scroll down to see the full list. We go all the way from Alabama down to Wyoming. In column B, I've shown you the populations as determined by the 2010 census. Adding them all up, we get this figure that we've seen before, the total apportionment population of about 309 million. Now, what we did at the beginning of the Hamilton method is to divide each one of the populations by the standard divisor, 710,767, and to round down or to give the automatic one seat. And for almost all states, it's a matter of rounding down. For example, if you do this for Alabama, the quota will be between 6 and 7, so when you round down, you get 6. And we do this for all the states. For example, for Ohio, when we do this, we come up with 16. For Wyoming, we give it its automatic one seat. Now add up all these numbers, these lower quotas or these automatic ones, and as you expected, you didn't give out all the seats. You gave out 415. You're supposed to give out 435. Now Hamilton says, oh, okay, so you've got 20 leftovers, and you hand out the 20 leftovers according to what he says. Jefferson says, I don't want to do that. I don't want to have leftovers. What I should do is to use a different divisor. Now, with the standard divisor, when we do these divisions and the rounding down, we get a total of 415. That must mean that we're dividing by something that's too big. right? So let's divide by something smaller. Let's try 700,000. Okay, and this will be automatically recalculated now. It'll do the same thing as before. It'll divide each state's population by the divisor and then round down. So here we see. Okay, so some things have changed. Some states have picked up an extra seat. You can see, for example, Texas right here, instead of getting 35, is now getting 36. In fact, 6 extra seats have been handed out, and now we've handed out 421. But that's not enough. We want to get to 435, so that means, in fact, we have to make the divisor even smaller. Let's try 690,000. When we do that, still we're only giving out 425 seats, so we need to make it even smaller. You see how we're just guessing and then checking with the help of the spreadsheet. And when we try 680,000, still we haven't given out enough seats. Let's try going down to 675,000. And now you see we've gone too far. Now we've made the divisor too small. Now we're giving out 435, just a couple more than we're supposed to. So let's try to go back up now. Let's go up to 677,000, shall we say. Let's try that. And that works, okay? So by a process of guess and check, we have come up with a divisor such that when we apply Jefferson's rule of rounding, we give out exactly the correct number of seats, 435. Now you might want to look and see how various states have made out. First of all, let's see Ohio. Okay, so Ohio was getting 16 initially, but now under Jefferson's method we're getting 17. So we're probably pretty happy about that. As another one to look at, let's look at the state of California. And this is kind of interesting. To begin with, California was getting its lower quota of 52, and Hamilton may or may not have given it one more seat, but it would get either 52 or 53 by the Hamilton method. However, Jefferson's method of changing the divisor has pushed it up to 55. California has 55 representatives, according to the Jefferson method. We're still looking in the spreadsheet. We're going to now look at the Adams apportionment. And this time, when we use the standard divisor, well, because we're using the Adams rounding rule, which says round up, everybody's going to be getting their upper standard quota. There's no need to worry at this point about anybody getting their automatic 1, because if you round up a number between 0 and 1, you will get 1 anyway, so you don't really need to worry about that. Notice, of course, that Ohio is getting 17. And when we look at the total, we see, oh, we've given out too many seats. Okay, we've given out 462 seats. That's too many. So what do we need to do to fix this up? Well, we need to now increase the divisor, okay? The divisor we're using is not big enough, so let's try 730,000 instead of 710,000. Well, even that isn't big enough because still there's 446, so let's go up to 740,000. See how that works. Still not enough, so we have to increase the divisor even more. And this time we were pretty lucky. When we got to 750,000 as our divisor, that's exactly one that will work. That's an appropriate Adams divisor. It exactly gives out 435 seats. You might want to see who did well under this method. Let's look, for example, at Ohio. Ohio now it gets 16 under the Adams method. Also, let's look at California. California is now getting 50, less than its lower quota. Okay, you can see the evidence here of what I said earlier, namely the Adams method doesn't favor the larger states, it favors smaller states. Now, how could there be another method? There is another method, the Webster method. Well, it's something of a compromise between Jefferson and Adams. And the method named for Daniel Webster says don't always round down, as Jefferson would tell you to do, and don't always round up, as Adams would tell you to do. It says round in the way you learned in elementary school, round to the nearest whole number. So if the fractional part is less than a half, you round down, and if it's a half or more, then you round up. Again, we will look at the example in the spreadsheet. Well, you know the drill here. First of all, we're going to try the standard divisor. Now here, we don't know if the standard divisor will work or not. We might be lucky and it might work. So what we're doing is we're taking each one of the state's populations and we're dividing by the standard divisor, and then we're rounding, well, not necessarily up or not necessarily down. We're rounding in the way that you learned in elementary school. Except, of course, if there's anybody that's below a half, they're going to get rounded up to 1 anyway. I don't think that actually applies to any state. There's no state that small that its quota would be less than a half. All right, so let's see. Let's take a look at Ohio. As we go by Ohio, we see, well, we're getting 16, as we knew, because our fractional part is less than a half. Now, let's see. What we want to check is at the bottom, how many have we given out? And it's very close to being correct. Not quite. It's 433. You see, with the Webster method, there's no guarantee ahead of time whether we're going to have to adjust upward or downward. We have to actually see how it comes out. When we see how it comes out, we can see, oh, we didn't quite give out enough seats, so that means we need to reduce it, but probably not by much. So let me try going down to 705,000. And in fact, that's already too far. Even that's not good enough. So let me go a little bit less. Let's go 708,000. And that turns out to be one that works, okay? So there is an appropriate divisor for the Webster method. It's 708,000. Now that didn't change things very much from what we had with the standard divisor. In particular, Ohio didn't change. It didn't get 16. And in fact, there must have been only 2 states that got 1 extra representative when we changed our divisor. It may be a little bit hard to spot where they are. Let me see if we can discover at least one of them. Oh, here's one. Minnesota. It turns out that Minnesota, when you make that slight change in the divisor, goes from having 7 to having 8, and there must be one more somewhere else. Here it is, North Carolina. Okay, those are the ones that got their one more seat when we adjusted the divisor under Webster method. Now, after all of this, you may well ask, well, what's the method that's actually used? Do we use Jefferson? Do we use Adams? Do we use Webster? And the answer is no. We don't use any of those. We actually use something that's called the Hill-Huntington method. We've been using that method since the 1940s. Now, it's very similar to the Webster method. It will give very similar results. Again, you may round either up or down. So how could it be different? How could there be yet another rounding rule? Well, amazingly enough, there is. Webster says, for example, suppose you have a quota between 1 and 2. If it's less than 1.5, then you should round down to get 1. And if it's 1.5 or more, you should round up to 2. In other words, this is a rounding rule in which the cutoff point is halfway between the integers. Halfway between 1 and 2 would be 1.5. For some strange reason in the Hill-Huntington method, you don't use that as the cutoff point. In fact, the cutoff point is, believe it or not, the square root of 2, which is about 1.414. If you're taking something that's between 2 and 3, a quota between 2 and 3, it turns out that the break point between rounding down to 2 and rounding up to 3 is the square root of 6, which is 2.449, slightly less than 2.5. In general, the cutoff point between rounding down to n and rounding up to n plus 1 is a number called their geometric mean, which is the square root of n times n plus 1. Now, this may seem like a very weird thing, but there are good mathematical reasons behind this. You say, what would be a natural criterion for deciding whether a method is fair? And if you come up with a certain criterion, it will lead you to this crazy decision that this should be the way in which you do your rounding. with the break at the geometric mean. This is the method that's actually being used and probably will be used forever for apportioning the House of Representatives. As I said, it's very similar to the Webster result, and if you try out the two methods on the 2010 census, they just disagree over a single seat. I actually forget who lost it, but in fact Rhode Island gets an extra seat that it wouldn't have under the Webster method when you use the Hill-Huntington method instead. Now there's one other thing that you may be wondering, which is, this is just guess and check. Isn't there any way to do it systematically? Do they just have people at the Bureau of Census guessing what the divisor should be? And the answer is no, they don't actually do guess and check. You can actually figure out exactly at what value of the divisor the apportionment changes. And based on this, you can draw up something that's called a priority ranking. Now, since the first 50 seats are handed out automatically, right? Every state is supposed to get a seat. Those first 50 should be thought of as handed out. So the priority list starts with seat number 51, and surprise, surprise, it goes to the largest state. If there were 51 seats in the House of Representatives, the 51st seat would belong to California. That is to say, every other state would have one seat and California would have two. What about if there's 52 seats? Well, then the next seat, the 52nd seat, goes to the second largest state of Texas. But if you would have a 53rd seat, it doesn't actually go to the third largest state of New York. California is such a gigantic state in population that it gets to cut back in line again and get seat number 53. And then New York will get seat 54. So you can make up this priority list and extend it as long as you like. You just happen to cut it off at the size of the house that you want, which is 435. I'm actually going to show you a proportion of the priority list from the 2010 census. And here it is. As we said, seat number 51 belongs to California. And you can say exactly at what value of the divisor this seat will be awarded. If you take the divisor and drop it down from some incredibly high value down to about 26 million, then in fact California will qualify to get a second seat. Okay? And then Texas deserves the next one, and California comes back in line. It's awfully greedy, but it's a huge state. So it gets seat number 53. Then New York gets a seat. Then Florida gets a seat. Then California again gets a seat. You can see California's in this list an awful lot. You have to go all the way down to seat number 61 to say, oh, Ohio deserves that one. Okay, that's where Ohio falls. So Ohio's seat number 2 is the 61st one. Ohio doesn't show up again until we get to 79. Okay, but we have this whole list. California appears there a lot. The bigger states appear a lot. The smaller states come in less often. And you just continue this down until you reach number 435. So you can see Ohio is getting its 16th seat when we reach number 418. And then it turns out that Minnesota was somewhat lucky. Minnesota is exactly getting the last seat that's handed out. And then North Carolina was somewhat unlucky because we've already decided the size of the house is 435. If there was one more seat, it would belong to North Carolina. What about Ohio? Where would Ohio be if we were handing out extra seats? Well, it turns out that Ohio would be back in line again for seat number 443, but it's too bad there aren't that many seats available.